So in our last video, we talked about how to do MPI gather and scatter. Um, those are collective communications that actually allows you to sort of send different pieces of data and gather different pieces of data to and from uh, different processes to like one process. So here is a diagram for MPI gather. So we have like 4 different pieces of data located on 4 different ranks, and then by doing an MPI gather, we can collect all those different pieces into like one rank. In this particular example, it's rank 0. So on rank 0, after the gather, on rank 0, we have all 4 different pieces, right? And uh, and uh, and uh, and uh, and there is another operation that's related to gather, but it's called Allgather. Allgather is a diagram that looks like that. So we have 3 different ranks in this particular example, 3 different ranks, right? And on each of the different rank, we have a different piece of data. So on rank 0, we have a red box. On rank 1, we have a green box, and on rank 2, we have a blue box. So if we are just doing a gather, for example, if we just want to gather all 3 different pieces to like one rank, say rank 0, after the gather, rank 0 is gonna have 3 pieces: red, blue, red, green, and blue, right? But Allgather is something that looks like this kind of diagram. So it's not just rank 0 is gonna get all the pieces, right? Rank 1 is also gonna get all the pieces. So rank 1 will also get all the 3 boxes: red, green, and blue. And then rank 2 also gets 3 pieces: red, green, and blue. So Allgather is just like a gather followed by a broadcast, right? So if you actually do a gather to rank 0, then rank 0 has 3 pieces, right? And then if rank 0 actually does a broadcast after its gather, and then propagate the same information to every other rank, then every other rank are gonna have the 3 pieces also, right? So Allgather is just like a gather followed by a broadcast, but by using Allgather, you actually complete the entire calculation, entire communication in a more efficient way. So Allgather is a is a slightly more efficient way for doing for doing this kind of gathering. And now let's look at its syntax, right? So Allgather, that's the name of the function, and then it has to be applied on a communicator, right? And then you need a CN buff, the address of the CN buff, starting address of CN buffer, right? So the CN buff is on rank 0, the CN buff is just the red box. On rank 1, the CN buff is just the green box. And then on rank 2, it's the blue box. And then CN count. So how many numbers are in each of the red, green, and blue boxes, right? So they must be identical. The size of red, green, and blue boxes must be identical. So that's the CN count. And then you have the CN type, right? And then you need a receive buffer, the address of the receive buffer. So the receive buffer for this particular example must be like the size of 3 of those boxes, right? So on rank 0, you must have a receive buffer that's allocated for the entire space of red, green, and blue boxes combined together. And then on rank 1, you must have a receive buffer that has allocated the same amount of space as red, green, and blue boxes. And then you have to do the same thing on rank 2. And then receive count. In this case, the receive count is not really the the receive count is not the size of the entire allocation for the 3 boxes. It's the receive count is it's actually the size of the information you can gather from individual ranks. So receive count must be also the same size as one box. So right, it's the size of the red box, or the size of the green box, or the size of the blue box. It's not the combination of all 3 boxes. It's just one box. It's the size of one box. It's the size that you gather from one individual rank, and then the receive type. So now let's look at how we can actually write this code. So we're gonna write an example code that's gonna implement this kind of a communication style. So let's just let me make a directory. Let me make a directory. Let's call it Allgather. Allgather, and then I'm gonna go into that directory. And let's try to create the code. I'm gonna use emacs nw allgather.cpp. So let's start to write the code, and I'm gonna include all the libraries from the C standard library, C++ standard library. So let's assume that we're gonna send out 2 pieces of integers from every rank, right? So that's the number of the send count ns. We're gonna call our send count ns equals to, let's just call it 2. Let's go to give it some arbitrary number, and then the total amount, the total size of the receiver buffer is gonna be controlled by ns times MPI size. So the receiver buffer must have this many ANR, this many integers. So we're going to use this number to allocate the space for our receiver buffer. And so let's try to create our send buffer. Let's call it send buff. And it's going to be this many. We're going to initialize the send buff with this many integers, right? So ns is 2, and then the initialization value, we're just going to initialize to MPI rank. So rank 0 is going to have MPI rank that equals to 0, so its send buff is going to be initialized to all zeros. And then for rank 1, its send buff is all going to be initialized to 1. And then for rank 2, all its send buff is going to be initialized to 2. And then let's initialize our receive buff. So it's going to have a size of NR, right? NR. And then because receive buffer is going to collect all the integers from all the ranks, right? And let's initialize to 0. Let's initialize the entire vector to just 0. And then let's just call our Allgather. Allgather. And then the send buff, the address of the send buff. And then the count, the send count is 2. So AS. And then the type, send type, MPI int, right? And then the address of the receive buff. And then the receive count. Again, the receive count is the receive count from each of the different ranks. It's not the entire size of the receive buffer. It's number of integers you are going to receive from each of the different individual ranks. And then the receive type, MPI int. So if we want to check the results, let's do some screen printout. So rank, MPI rank, receive buff, and then let's just loop through everything. Let's do a rangeful. separated by space, and then end of line, and that's our code. And let's try to compile it. MPI plus plus std equals to c plus plus 14 dash o allgather.cpp, and then MPI run. Let's use 8 processes, and that's our result, right? So each of the different rank is going to send out 2 integers, and the value of those integers are going to be the same as the rank, and then those two integers are going to be gathered together into 16 numbers, basically, into a vector of 16 integers, right? And that's the 16 integers, right? So we got like 2 zeros, that's from rank 0, right? And then 2 ones, that's 2 integers from rank 1. And then 2, 2, 2, 2, 2, 3, 2, 4, 2, 5. So it looks like the result is correct. So that's Allgather. And Allgather also has a version that's Allgather also has a version that's vectorized. So not exactly vectorized, but for now, all the Allgather function only takes the same amount of data from each of the individual ranks, right? Suppose you want to contribute a different amount of data from different ranks. You have another alternative that's called Allgather v, and Allgather v looks like this kind of a call. So the function signature looks like that. So you have a send buff, right, and then send count, and then you have a send type receive buff. But on the receiver side, you have to sort of know an array of receive counts, basically. So it's the amount of data that's coming out of individual ranks, right? So here it's not just a one number anymore. It's an integer array, right? That gives you the receive counts. And then you also need to know the displacement, the offsets of each of the numbers that's contributed by each of the different ranks, and inside of the receive buffer, basically. It's an offset inside of the receive buffer in order to actually the starting location in the receiver buffer from which the ranks, the data contributed by each of the different individual ranks is going to be located, and then the type, the data type, right? And that's sort of the syntax. But now let's look at a concrete example. Let's look at one concrete example. So so it's called Allgather v. Let me create a directory. It's called Allgather v, and then I'm gonna go into that Allgather v, and then try to edit a file that's called allgatherv.cpp. Oh, so I am actually inside of Emacs already, so all I have to do is to Control XF allgatherv.cpp, right? Um, so in order to actually do this example, let me just write the code, and I'll try to explain later on. this part is actually identical to every other MPI example we've done so far. And so how I'm gonna construct this particular example? So each individual rank is gonna contribute a different amount of data. So what's gonna be the number of integers we're gonna contribute from each of the different rank? We're gonna ask each rank to contribute. So the set count s is gonna equal +1. So 0 is gonna contribute one number, right? And then rank 1 is gonna contribute two numbers, and then rank 3 is gonna rank 2 is gonna contribute three numbers, right? And then rank 3 is gonna contribute four numbers, that kind of thing. Same count. So each different individual rank is gonna contribute the rank ID +1, this many numbers, right? And then our CN buff. We're gonna initialize it to ns, and then the value we're gonna use for CN buff is just gonna be MPI rank, right? So rank 0 is gonna be one number, ns equals to 1, right? And then that number is gonna be initialized to 0. And then rank 1 is gonna be two numbers, and then that number is gonna be initialized to, those numbers are gonna be initialized to 1, right? And then rank 2 is gonna be three numbers initialized to 2, that kind of thing. That's gonna be our CN buff. And then we need to construct a vector to store the receive counts. So how many numbers are coming out of individual ranks, right? That's different. That's different for different ranks. So we're gonna need a vector in order to actually store the receive counts. So the size is gonna be MPI size, right? Receive counts is gonna have this many numbers because we have this many ranks. And then let's initialize it to 0 first, right? Let's just initialize all the receive counts to 0. Right? And this receive counts is allocated on every rank because it's Allgather, right? It's Allgather. So by the end of the Allgather V, every rank is gonna have a receive buffer, and every rank must know the receive counts from every other ranks, right? But in order to actually populate the receive counts vector with the correct numbers, we have to do a gather. We have to do an ordinary gather. It's not a gather V. The reason it's not a gather V is because the receive counts vector, every element inside of the receive counts element vector is just it's basically just the CN counts from every different rank, and that's just the one number. The CN counts is just the one number, right? So this, in this case, it's an ordinary gather. It's an ordinary Allgather. So the number we're sending is ns, right? Ns equals to 1 on rank 0, ns equals to 2 on rank 1, and then equals to 3 on rank 2, right? So different numbers on different rank. And then it's just one number, and then MPI int. The type is MPI int. The receive buffer is going to be receive counts. The address of it, and then MPI int. Right. So that's going to be the receive counts, right? And then we also need a vector to store the offsets to the receiver buffer, right? The displacement vector. So vector int displs. It's also going to be MPI size, and we're still going to initialize everything to 0. So we can actually compute the displacement vector from the receive counts vector, right? Because if we know the number of integers that's contributed by each of the different individual ranks, then we know its offset into the receiver buffer, right? So all we have to do is to do an accumulation for auto I goes from 1. It's not from 0, because the offset from the zeros so the offset for the numbers from rank 0 is always going to be 0, right? Because the the numbers contributed by by rank 0 is going to be located at the beginning of the receiver buffer. So the displacement into the receiver buffer for rank 0 is going to be 0. So that's why we don't need to sort of and the displacement vector is already being initialized to 0. So every number for now inside of the displacement DISPLS vector is going to be 0. So we don't have to change the first element. And then I is smaller than MPI size, and then plus plus I, and then DISPLS I equals DISPLS I subtract 1 plus ICV counts I subtract 1. So this way we have constructed our displacement vector. Also need to know the total number of integers we're gonna gather to every rank. Right? The reason is that we need this number in order to allocate receive buffer. We need to know how large the receiver buffer needs to be. So how do we actually get So all we need to do is to actually get a summation of all the numbers that's in the receive buffer, receive counts, right? All we need is just a summation of all the numbers in receive counts. So how are we going to do that? We're going to define the total number to be n num. N num is we're going to use a C++ intrinsic. It's not exactly intrinsic. It's an algorithm that's inside of the template library that's called accumulate. This accumulate function takes 3 input parameters. The first one is the iterator, the beginning iterator. And then the end iterator. And then the initialization value of the accumulator. And then n is going to in receive counts. Here we have used a standard template library algorithm called accumulate. And if you are not familiar with this particular function, you can sort of look it up by just googling, right? And then we know how large our receiver buffer must be. Receive buff and num. Let's initialize every number to 0 first. And now we're ready to do our gather v call. So MPI Allgather v. Gather v. Then it's going to be the send buff, the address of the send buff. And then NS is going to be the send count. And then MPI int. That's on the send side. On the receive side, we have the address of the receive v buff, right? And then we also need the address of receive counts. And then we also need the address of DISPLS displacement vector. And then the type is MPI int, right? And we're done. Suppose we want to print out the numbers we have gathered. This is just for checking the results. So for auto inside receive buff, we're gonna do a print out of I, and then see out end of line. Allgather v. So let me compile it. Allgather v, and then Allgather v.cpp. Receive counts. DISPLS. Got some typos. So it must be receive counts here. DISPLS. Let's run it. Again, use 8 processes. So that's the gathered results. So So rank 0 is going to contribute one number, and that number is 0, right? And then rank 1 is going to contribute two numbers, that number is 2. The value is 2. Rank 2 is going to contribute three numbers, the value is 2. And then rank 3 is going to contribute four numbers, and the value is 3, right? And that's indeed correct. So that's Allgather and Allgather V. Allgather and Allgather V. Two different kinds of collective communication styles. And now let's look at the next example we want to try out. We're gonna compute the standard deviation in parallel, right? So in this particular example, we're gonna look at one more collective communication that's called Allreduce. Allreduce looks like that. So you have a bunch of, for example, you have so in the ordinary reduce, you just reduce the results to like one rank, right? If you have like a if it's just the reduce operation is called MPI sum, right? And if you're actually reducing it to like one rank, for example, rank 0, then rank 0 is going to have the reduced result, but every other rank is not going to have the reduced result, right? But Allreduce is just like a reduce first and then broadcast next, right? So again, we are doing an MPI sum. Reduction operation is the MPI sum, and we have two numbers located on every rank, right? So if it's just the ordinary reduce with the MPI sum, and if you reduce it to rank 0, then rank 0 is going to have two numbers, right? The first number is going to be a summation of the first number on every rank. That's 5 plus 2 plus 7 plus 4. That's 18, right? And then the second number is going to be a summation of all the numbers, the second number on each of the rank, right? It's 1 plus 3, and then plus 8, and then plus 2. That's 14, right? But now Allreduce means that once rank 0 gets the two numbers, the reduction results, it wants to broadcast it to every other rank. So every other rank is going to have the same information, the two pieces, the two numbers, 18 and 14. So 18 and 14 located on every rank. And the syntax is like that. You need a send buff on every different rank. You're going to have a send buff that's going to be used to store the two numbers. And then you're going to have a receive buff. The receive buff, if it's an MPI sum, for this example, receive buff is going to be two numbers. And both send buff and receive buff must have the correct size, the correct memory size on every rank, basically. And then the count, how many numbers, right? How many numbers? 2 in this case, right? The data type, integers in this example. And then the operation, that's MPI sum. And we are going to use this operation in our calculation for the standard deviation. But the calculation is going to be carried out in parallel. So what exactly is the standard deviation, right? So first, in order to actually compute the standard deviation, basically measures the width of a certain distribution. So here it's a normal distribution, right? And this normal distribution has an average, has a mean of 0, right? And then the width is called the standard deviation. So how do you actually compute it? The first thing you have to sort of compute is actually the mean. That's the mu here. The mean is basically a summation of all the numbers, and then divided by the total number of numbers, right? That's the mean. That's the average of all the numbers. And then in order to compute the standard deviation, you have to sort of subtract the mean, right? Here, that's one of the numbers, right? One of the numbers that's called xi. Subtract the mean, you get the deviation of xi, and then you square it. You square the difference, and then do a summation over all the I, so over all the numbers, and then you get the average of the squared summation of the differences, and then you take the square root. That's the standard deviation. So in order to actually compute the standard deviation, you will need to know the mean. But because the calculation is carried out in parallel on many different cores, so each of the core is just going to hold a subset of the set of numbers xi, basically. So rank 0 is going to store x0 to say x10. then rank 1 is gonna store x11 to x15 or something, right? So every different rank is gonna store a different subset of all the numbers. So in order to actually compute the mean, the average, what you need to do is basically a reduction, right? You need to sum over all the numbers that's located on every different rank. That gives you a partial summation. The problem that we solved in our first example, a partial summation, right? And then you need to do a reduction in order to actually sum up all the partial summations into a global summation. Once you get the global summation, you divide by the total number of integers, and then you get the average, right? But that kind of reduction is just like before, right? It's you can do that just like before using a just normal reduce, right? But the problem is that if you just do a normal reduce to reduce the mean to just a one process, how are you going to compute the standard deviation on every other ranks, right? You have to sort of reduce the mean to every rank so that every rank can use that mean to compute this kind of partial summation of the difference of its number and the mean, right? Of its numbers and its mean, and then do a square, and then do a local summation of the difference, the squared difference, right? And then you can do a global summation of the squared difference, and then divide by big N, and then take the square root to get the standard deviation, right? So that's going to be our approach. So we are going to first do to compute the mean, and then when we do the reduction, we do an Allreduce. So that every rank is going to have a copy of the mean, and then following that, every rank can do its own thing to compute its partial local summation of the squared difference, right? Once the local summation of the squared difference is obtained, we do another reduce. This time it's going to be a normal reduce. We're gonna just reduce it to like one rank 0, right? And then we're gonna get the global summation of the square difference, and then we divide by n, and then take the square root. So that's gonna be our strategy. We're gonna sort of try to code it. Let's call it Paro stddev. Paro stddev. That's our directory. Let's go into Paro stddev, and then I'm gonna just do a Paro space std. So before I write the main function, let's try to generate some random numbers. I'm gonna need a integer random number generator, and then a floating point random number generator. The floating point random number generator is just for generating those xi, so I can compute the mean of those xi's. So if you don't remember, so I need a set of xi's. In fact, I need a big N, this many xi's. And so that's we're going to use a floating point random number generator for that. And in fact, we're going to generate a normal distribution basically. All the xi's generated by our random number generator are going to follow a normal distribution with a user specified mean and user specified standard deviation. That's sort of the expected mean and expected standard deviation. And then we're going to compute the actual standard mean and actual standard deviation, and then we're going to compare it with the user input. And then we're going to need a integer random number generator, because I want to make every different rank to generate a random number of random number of so get random int, and then I'm going to specify a range int min, int max. So all my random integers are going to be between min and max inclusive. So I'm going to use the recommended way of generating random numbers. Random device first, and then MT, the random engine, MT19937. I'm going to RNG random engine, and then the RD as the constructor input, and then I'm going to use a uniform int distribution. Then takes template parameter int. I'm going to call it uni, and then the distribution is from min to max, and then it's going to be RN. That's going to be our integer, and then I'm going to need random number generator. The output is going to be just a double get random double, and then it's all take two double as inputs, in, and then a double std dev. So those are expected min and expectation. Again, random device, random engine. But this time it's not going to be a uniform distribution. I'll use a normal distribution. And it's going to be a double normal distribution. And then I'm going to call it normal. And then min std dev. And then I'm going to return normal RNG. So that's my two random numbers. So now I can write my main, which is kind of similar as before. Finalize. ARGC, ARGV. Right. So auto MPI size. And then auto MPI rank, MPI WRLD dot get rank. I'm gonna define two doubles. One is called expected min, initialized to 0.0d, and then another one is the expected standard deviation. And then if the rank is 0, if MPI rank equal to 0, I'm gonna try to gather this expected min and expected standard deviation argument. So I'm gonna so expected min is gonna equal to A to F ARGV1. Then std dev is gonna equal to A to ARGV. Right, that's the two standard arguments. And then mmwre dot b expected min 0. Expected. I'm gonna do a bcast. And then auto. So NL is gonna be the number of random floating point numbers that we're gonna generate on each of the different ranks, right? And that's gonna be an integer, right? So we're gonna get this from a random number generator, random int. Let's just try to generate 100 to 200. So each of the different rank is going to generate this many NL, this many uh, random floating point numbers. And NL is going to be between 100 and 200. It's going to be a number that's between that. And then we're going to need a vector of doubles to store all the random floating point numbers. And the size is going to be NL. Let's initialize it to 0.0. Now let's populate the random vector. So again, I'm doing a range 4. But here I'm actually using a reference. So the iterator is going to be a reference to all the random local vectors. By using a reference, I can change the values of the vector directly because it's a reference. It's a handle, so I can change its value directly. So v is going to equal to get random double expected mean and expected stddev, and then auto sum local. Right. Once I have finished populating the random vector on each of the different ranks with a normal distribution of the that's specified using the expected mean and expected standard deviation, we can do a summation. We can do a summation of all the numbers, right? And then I'm going to use the accumulator. So this is the standard. This is the algorithm that's inside of the C++ standard template library. Rand local. That's the beginning iterator. That's the ending iterator. And then all I have to do is the accumulator starts with 0.0. That gives me the local summation, right? Once I have the local summation, I can actually try to reduce the global summation, right? So let's try to define a sum global. And then it's going to start with 0.0d. We're going to initialize it with 0.0d. And then we also need to know the total number of floating point numbers that has been generated by all the different ranks. We're going to call it num global. Initialize it to 0. So we're going to do like 2 or reduce. So or reduce sum local, that's the send buffer, and then sum global, that's the receive buffer. 1 MPI double, and MPI, the operation is going to be MPI sum, right? So this way we get the global summation. In addition to that, we also need to know the total number of floating point numbers generated by all the so we're just going to copy this particular line here. So the send buffer is going to be NL, and then the receive buffer is going to be num global. 1, it's supposed to be an int, and then MPI sum, and it's all reduce. It's actually all reduce. Both of them are actually all reduce, right? So after this all reduce, after these 2 all reduce calls, so every rank is going to receive the global sum, the correct value of the global sum, and every rank is going to receive the correct value of num global, right? So once every rank actually has these 2 pieces of information, it can actually compute the mean, right? The mean global. So let's call it mean global. It's going to equal to sum. Every rank can actually get the mean global. So once it's equal, we can every rank can start to compute its every rank can start to compute its summation, its local summation of the squared difference, and that's what we are going to do. So the squared difference square sum local equals to 0.0 d. and then for auto v is going to inside rand local square sum local plus equal to v subtract mean global times v subtract mean global. Right. So v is still a vector that's going to range through every different values inside the local random floating point vector, and then every v is going to subtract the mean global, that's the average, and then do a square, right? Do a square, and then the squared difference is going to be accumulated to square sum local, right? And then all we need to do is to compute the square sum global. Let me correct the typo here. Square sum global. And again, we're going to use a reduce, but this time it's going to be a reduce just onto the zeros rank. So it's going to be a normal reduce. So square sum local, that's going to be our send buffer. And then the receive buffer is square sum global. And then it's going to be one number and MPI double. And then the operation is MPI sum. And then we're going to reduce it to rank 0. That's a normal reduce code, it's not an all reduce, right? It's a reduce, it's not an all reduce. So only rank 0 is going to get this, it's going to get the correct value for the square sum global, right? So once the rank 0 actually gets square sum global, so this part of the code must happen on just the rank 0. It cannot happen on every other rank because every other rank doesn't have the correct value for square sum global. So on rank 0, so we must place this part of the code inside of this if branch. So auto std dev is going to equal to sqrt, the square root function, square sum global divide num global to the number floating point numbers, and then we're going to do a cout mean global, and then standard deviation std dev end of line. And let's compile it. MPI C++ std equals to C++ 14-0 parallel stdv and parallel stdv.cpp. Sum local. Oh, I have a typo here. It's in one of the all reduces. Low CA. So now let's try to run it. MPI run. I'm going to use 8 different processes. Parallel standard deviation, right? It's expecting 2 command line arguments, right? So the first one is going to be the expected mean. Let's just give it like some arbitrary number, say 10.5 or something, right? And then standard deviation, let's just give it like 5.2, right? And then let's see what's going to happen. So the mean is going to be 10.4626. It's really close to 10.5, right? And then the standard deviation is 5.23. It's really close to 5.2, right? So if we run it a second time with a different kinds of mean, let's give it like minus 21.6, and then the standard deviation is like let's give it like a 10, like 12.5 or something, right? So the mean is going to be minus 21.6 0.78, so it's kind of close, right? Not very close. The standard deviation is much closer. So, so that means that we have actually implemented our algorithm correctly. So that's Allreduce. That's Allreduce. And we have demonstrated Allreduce using this standard deviation, parallel standard deviation calculation.